We've been looking at the derivative of a function and looking at that as an instantaneous rate of change at anywhere on our function. That's what the derivative is. Or the derivative we looked at a particular value of x, and that was the slope or the instantaneous rate of change on the function at that value. And so in front of us, we have pictures of functions f of x. Those are 27, 28, 29, 30. I pulled those from your textbook. And then above are the derivative function. So that is the graph of the derivative of a function. And so we were going to try to figure out which graph matches, the function graph matches with the derivative functions graph. And so when you're doing this, it's really helpful to find when is our function increasing and when is our function decreasing. And so we know that f of x, our function, f prime of x, sorry, is greater than 0. So that derivative is positive when f of x is increasing. So if we could go on our function and find out all the places where our function is increasing, what x values the function is increasing, if our f prime of x is bigger than 0, then we know that our derivative function has to be above the x-axis here. So the graph of the derivative, so the graph of f prime of x is above the x-axis because it's positive. If we find that our function is decreasing, so looking at where our function is decreasing, that would tell me that the derivative, because that's a slope, if the function is decreasing, the slope is less than 0. So the derivative function f prime of x is less than 0 when f of x, our original function, is decreasing. And so if our value of our derivative is less than 0, this tells me the graph where my function is decreasing, the derivative function has to be below the x-axis. So the graph of f prime of x is below the x-axis. Other things that could help me determine which what the graph of the derivative would look like is looking at when is my slope, when is my function equal to 0, or when is the slope of the tangent line equal to 0. So f prime of x, the slope is equal to 0. This happens when we have max or mins. So this occurs where f prime of x, or I'm sorry, f of x has a max or a min value. It also could be our derivative is equal to 0 on constants. If we looked at a horizontal line, that slope is 0. And so it could be our graph is just leveling out and constant for a while, or we have the graph of a constant function. Or the tangent line has slope 0, which would occur on the max or the min. Well, if our derivative function is equal to 0 at these x values, then that tells me this is where f of x is equal to 0. My y value is equal to 0 for the derivative function. And so that's going to tell me that this piece of the graph for my derivative function is going to cross the x-axis or be a horizontal line on the x-axis for a while. So this is where the graph of f prime of x crosses or touches the x-axis. So what I would do is I would look at my first function, 27, which looks like a parabola facing upwards where the vertex is at the origin. And I would look at first, where is this graph increasing and where is this graph decreasing? I just snipped the f of x here, and it's a parabola again. Let's look at where it's increasing and decreasing. And so a lot of times in mathematics, we use interval notation. So we're using what values of x that we're starting from and to what value of x that we're stopping from. And usually use parentheses or brackets depending on if you're including or not including. Well, from the left, coming in from negative infinity until I hit 0. So from negative infinity to 0, I notice that my graph is going downwards if I'm moving left to right. So this is decreasing here. And so this is decreasing. So this means that my derivative function, that slope, f prime of x, has to be less than 0. And then if I look at where is it increasing, so going up from left to right, I can tell that it's in here. And so it's increasing from 0 to infinity. And that means my derivative function, if it's increasing, my slope is positive, so f prime of x is greater than 0. So I need to look for a function where of the pictures of the derivatives where my graph is strictly below the x-axis from negative infinity to 0 and above the x-axis from 0 to infinity. The other piece here is that I can see that I have a horizontal tangent line at this minimum. And so I can see that f prime of x is equal to 0 when x equals 0. And so I can see that then it's going to cross the x-axis. My derivative function crosses the x-axis at 0, 0. So f prime of x crosses the x-axis at 0, 0, which makes sense if part of it's below the x-axis until we hit to 0, and then above the x-axis when we hit 0. Unless there's a jump in the graph, it's going to have to cross the x-axis at 0, 0. So looking for those things, I would go back and see if there's anything that matches that. And so anything that is strictly below the x-axis from negative infinity to 0, I only see one of those, which is B. This is below the x-axis until we hit 0, and then above the x-axis from 0 to infinity, and it's crossing the x-axis at 0, 0. None of those other graphs, those conditions don't hold. And so I would say that this graph, which was 27, the derivative function was equal to the graph B. So let's look at another one. Okay, so I just pulled the second function f of x, and it looks to me like a cubic function. And notice that if I'm looking at this graph is pretty much strictly increasing. Kind of levels out here. This kind of looks to me like a horizontal tangent line for a little bit. And then it starts increasing again. So what that's telling me is that my derivative function, f prime of x, is greater than 0. It's positive from, let's say, negative infinity to 0, and then union from 0 to infinity, not really including 0. So that little piece here at 0, this is where our tangent line is equal to 0. So f prime of x equals 0 when x equals 0. So I know that my derivative function, when I'm looking for it, has to be above the x-axis everywhere except for 0. I'm going to have a point at 0, 0 on f prime of x. This is above the x-axis. So I would go back to the graphs of the derivative and I would look to see is anything strictly above the x-axis except for 0, 0. And so if we do that, notice that A, the parabola, is strictly above the x-axis and we have a point at 0, 0. So for 28, f prime of x is equal to graph A. So 29, that graph is a wave function, and it looks like the cosine function to me. And it's increasing and decreasing an infinite number of places. And so I know that also I have a lot of max and mins here. So every time I have a max or a min, that's where my slope of my original function is 0. So we can see that f prime of x equals 0 at max and mins. F of x. So these are going to be the places where it's going to be crossing the x-axis. So crosses x-axis here. Or f prime of x crosses the x-axis here. And then it's decreasing or increasing in between there. And so I don't know if this is the cosine function or not. If it was, this would be, what would it be? Negative 2 pi. This here would be pi. It's hitting at, sorry, I need to think about it for a second. Backwards. Sorry, this is negative 3 pi halves. This would be pi. This would be 0. And this right here would be pi halves, negative pi halves. And so these would be the places where it'd be crossing the x-axis. So negative 2 pi, add a pi, at 0, negative pi, 0, pi, 2 pi. See, we should be able to write that mathematically. This is going on forever. So I could write that mathematically, right? This is the sequence where I'm multiplying some integer d times pi, where b is an integer. And then decreasing. Well, it's decreasing from negative 2 pi to negative 3 pi halves. It's decreasing from 0 to pi. These are coming in forever. Union, and then it's going to be decreasing again from 2 pi and then add pi halves to that. So what would that be? For 5 pi halves. Dot, dot, dot. Okay, so can we just go back and look at the graphs, and we know that's increasing in the other spots, and see if we have things that are multiplying or going through these x-axes at multiple places, at these places, and are decreasing. So if I go back up here, so places where it's going through multiple places are here. And remember back at the other graph, or what I said looked like a cosine, that was where the horizontal was. It's passing the x-axis there. Okay. So this graph here, f prime of x, is equal to graph D, which should mean that power of elimination 30 should be C. And we could quickly look at it. It's decreasing everywhere. So this should be below the x-axis until we hit this value here, where it's going to cross the x-axis. So note this is below the x-axis. We're crossing the x-axis. This piece here now is going to be increasing until we go to 0, which means my derivative function is above the x-axis, which it is. It's that piece here. And then notice that this is a horizontal max. It's going to cross the x-axis there or touch it. This is decreasing, so it's going to have to be below the x-axis until I hit this min. So it does go below the x-axis until I hit the min. And then when it's increasing the rest of the piece, this has to be above the x-axis after that min, which it is. And so it does match up. And so I can say that this graph f prime of x is C. So given an original function, you should be able to graph the derivative function. And again, looking at where it's above the x-axis, below the x-axis, thinking about slopes, max, mins is really helpful to do that.